Hello. All right, much better. Morning, everybody. And I. Um, so this time, actually, I have a co-author of what I'm going to present, and that's Sashi here. Sashi, will you just come up? So Sashi holds two positions. Firstly, he's my boss. He runs HF Signals, and I've gotten him here so that you can catch him rather than me about ZBTexes not being shipped on time. And he and I have actually worked a lot on this particular project, and we worked so much that we couldn't get the paper in time in the proceedings, and you'll know why that's happened. So he's here. I'm going to do the presenting, and if you have any questions in CW, he's going to answer them because he only speaks CW. He's actually jet lagging badly. So we are here now, and thanks, Sashi. But he'll be here as well during the evening, at the vendor night, as well as the homebrew competition, etc. So this is called QRP messaging system. And I'll just tell you what we mean by messaging system and why we require it. Two things here. One is that very often in our craft and art of radio building, we tend to forget about the fundamentals and the fundamental theory that is behind all communications. I'm talking about Claudia Shannon's work, etc. We are not going to dip into the maths part of it, the mathematics, but nevertheless, this will give you a sort of a quick, bites into what works behind the communication systems that we work at level of mathematics and science rather than the technology. So there are going to be no circuits. There are going to be no, rigs being shown here, although it works on ZBTX for the time being, and we hope to be able to port it into a system which works like WSJTX or like FLDigi very soon. So I will basically start here by a little bit of a review, and just hang in with me for this. The other part is that there will be a lot of stuff here which goes against the conventional wisdom, and more than wisdom, the values that people in this hall subscribe to. So I hope it's all right. So this is our regular, this has been my favorite rig since I was a kid. I always salivated over this. The FT8 works the world on a couple of watts, right? And this is what we've always tried doing. I hope to be able to pick this one up in Dayton this time. I haven't seen one for the last 2 or 3 years on sale anywhere in the flea market. But this is a radio that we all understand, right? There's a tuning knob, there's a volume knob, there are band switches. A couple of people who are born in this century may not realize what loading and preselector do, knobs do, but that's all right. There are very few of them here. But, if you actually look at what a modern radio looks like for us all, it's very different. It's this. There's no tuning knob, there's no volume control, right? I think there's a volume control. No, there is none. And it's very difficult. I tried operating this radio. This is a modern radio, right? This is the radio which is used by NATO. There's no tuning knob to it, much less a volume control. There is actually a volume plus minus. There are strange things instead of a band switch called CT, PT, CC, LD, and Z. And, okay. CT is basically encrypted text and plain text. And LD actually means that you load the frequencies that you're going to operate on. So there's no tuning knob, which is a good idea. If you're out in the field and somebody wants to do, snag a rare DX, which he's just heard, it's not a good idea when you're out in the field. So that's there. There are some remnants from the past. For example, on the top right of the display, you'll see that there is still an S meter, right? Which is there even on your phones for that matter. But otherwise, this is what most of the people, outside the amateur domain use for a radio, for a two-way wireless radio. So behind it all is actually something which we do not want to talk about. Okay? There are values and things that we do not want to even acknowledge that are dear to us. Okay? And one of it is that reliable communications. We do not want reliable communications, right? We want the excitement of a hunt, right? Where you go and pounce, or you lay in wait for a DX to creep by and you sort of jump on this and consume it. So reliability is one of the things that I want to talk about here, which is how do you make your messaging, texting, or CW to be far more reliable than it is now. I mean, can you send a message to your mom? You can't do that, even if your mom can operate a radio, because the propagation works, doesn't work, et cetera, et cetera, et cetera. But how about making it more reliable? In fact, how about making it like that? So this is what we're going to present now, which is a messaging system, very much like your Signal and WhatsApp, et cetera. And how do you get there from where we are right now with our radios? There are a lot of compromises, of course, and I'll tell you why these compromises are there, and then how do we overcome some of them, and what are the trade-offs with which we can live, which will still allow us to do reliable communications between our community. So just to get an idea of what we are up against is, if you took all the infrastructure, I mean, ours is really amazing that without any infrastructure, without there being fiber optical cables and Ethernet and underground sea cables and cell phones all over the place, we are still able to communicate with each other, right? We are very sovereign that way with our communication needs. But if you took just the optical fiber cable and laid them end to end, it would actually span the solar system. Okay, that's how large it is. That's the machine. It's probably the largest machine ever built by mankind that you could, there's so much of fiber optics, routers, et cetera, that you could actually span the entire solar system. And it costs about $2 trillion. Okay? So if you took a tuk-tuk in my city and paid it $2 trillion, it would take you to Alpha Centauri. Right? So that's the amount of infrastructure that we are talking about. And on the other hand, we have Mr. Adam here, 66 feet of wire, $100 radio. He's still able to do 6,000 miles, right? Which is really impressive, very, very impressive, what we do with our small radios. That's, I think, it's a QMX. No, it's not a QMX. It's the FCR4R or whatever, right, that he's using. But how do we transit from here to here, which is basically an instant messenger? So just to get an idea of what we are talking about in more objective terms, let me do a little bit of a calculation here. So imagine that these are the kind of messages that we are trying to send. I have marked as you see on the top 1, 2, 3, 4, 5, etc. That's basically to count the number of characters. All right. And in some of these messages, you'll see a plus before the message. I'll come to that in a bit. But the important thing here is that there is a 13-character message which says, at 11:30, I'm QRV on 14020, in case somebody wants to talk to me, right? Or call me up. Or I'm asking Sashi, at 2 p.m., meet at 1400 hours for coffee at La Makan, which is the place where we all hang out in Hyderabad. Or I say that my QTH right now, that's my location, is something. And or you say, hi, 10th or 11th, does that work for you? I'm reaching New York City on 5th May. And you'll see that this is all very compressed because I'm trying to save on the power. We're trying to be QRP here. A little bit of, fonts have gone up and down and, trying to get it onto the system. But you say, okay, how will you come? Take a bus, which is about 28 characters. There is another status update. They're saying QRL, I'm having my exams, I can't come along. So if you see all these messages, they are really short messages. And the statistics is that an average message on, let's say, WhatsApp or on Telegram or Signal is about 30 characters or less, okay? And imagine that the most important messages are about 10 being sent per day and 20 coming in. So if you calculate those, it's just 1 kilobyte of data per day and 2 kilobytes of data being received, which is really, really low if you look at it. And if you look at the speed, it comes to about 0.3 words per minute or 0.6 words per minute in order to be able to communicate this asynchronously. That's the whole point, right? You leave this message and you wait for it to go out or come in, much like QRSS. And we look at what are the options which will allow us to do this reliably. That is, you put the message in and then you wait and the message will get across, right? So what are our options to do that? So here are some of the options. CW, PSK, RTTY, and FT8, right? So those are the 4 options that we look at, and we'll see what works and what doesn't work here. So if you look at Morse, by the way, is not CW, okay? Morse is not continuous wave, it's on-off wave, it's on-off keying. We wrongly call it as CW, it's not CW. So actually with the human ear tuned into this, the bandwidth is about 20 hertz, which is why even now, the human ear is far better at reading CW than most of the decoders. And because it's going on and it's off half the time and on half the time, the signal strength is actually half of what you rate your transmitter as. So if you say your transmitter is 5 watts, what you're putting out is actually about 2 to 2.5 watts because the average power is that much, which is one problem. Second problem with that is that because it's an on and off, and there's fading, there is noise, etc. happening, it's difficult to know when it's off or on if your signal is just about hovering on the, just above the grass, just above the noise. So that's the problem with Morse, which is why, making it reliable is difficult. PSK31 has sort of, it's a little long in the tooth these days, but it takes about 100 hertz of bandwidth. The problem with that is it's a phase which is flipping of the same signal. So firstly, the amplitude is going up and down. If you've seen the waveforms of the PSK31, it resembles amplitude modulation. They're just peaks and troughs all the time. And it needs a bandwidth of about 100 hertz. And there are about 31 changes of phase per second, which is why you require about 100 hertz of space. RTTY maintains the output power at all times, right? It doesn't go on and off. Once you switch on, it just remains on all the time. What happens is that one tone is 0 and the other is 1, mark and space. So it basically shuttles between 2 tones or 2 frequencies. And the good thing is because you have got one bandpass filter on each of the frequencies, you can always compare the amplitude between the 2 to figure out whether it's a mark or a space, which is why actually RTTY, surprisingly, and in long-term experience, turns out to be actually better than PSK31, right? Even now you see a lot of RTTY contests, but very few PSK31 contests. So it's a surprising fact that RTTY has managed here. The problem with RTTY is that we basically took this from the teletype, which used to work at 45 baud, right? 45.5 baud or whatever. If we had slowed it down to, let's say, 10 baud or even 3 baud, it would have been a very, very reliable system. But unfortunately, that's not what happens. Then we come to FT8. Now, FT8 and the 8 in it says that there are 8 tones, right? Which are separated just by 6 hertz. They're just separated by 6 hertz each. And unless you're a trained music here, you can't actually make out the difference of the 6 hertz, right? But of course, a computer could do that, or mathematically you could do it. So it's within 50 hertz of bandwidth. And because there are 6 hertz suppression, you have to hear it for a long time. I mean, people who have tuned a guitar will know this, that on the bass strings, it takes a longer time for you to figure out whether you're on the note or off when you're trying to tune it. So it takes you a longer listening time to figure out what the exact frequency is. It's like this, if you have a frequency counter in which you're trying to figure things out to, let's say, 100 hertz precision, you can do it 100 times a second. But if you would like to measure a frequency down to the last hertz, you have to wait for a whole second for that to happen, right? So that's exactly what happens with FT8. Now, so we have chosen FT8, and I'll just delve a little deeper into this to firstly reason out why 8 tones are used on FT8. So this is going to be about 10 minutes of talk about FT8, because that's very relevant to what we are going to do here. And which is this, that if you consider a message as zeros and ones, right, and your message is entirely composed in binary of zeros and ones, and each combination of zeros and ones comes to a character or a letter, which is what even CW does, right? If you consider dot and dashes as zeros and ones, you could actually translate that also into a binary sequence. So let's look at this. There are 8 tones spaced out by 6 hertz each. Now, when there are 8 tones, each tone can actually, for example, you say that starting from 200 hertz, 206, 212, 18, 24, 30, 36, 42, and 48 are the 8 tones. And these 8 tones can represent a combination of 3 bits, right, whatever they are. But you can have 8 distinct, combinations of zeros and ones, which the 8 tones can represent. Now, if you had more tones, for example, if you had 26 tones, you could have represented a letter of alphabet with each of those, right? So you could keep doing this, and you could go to 26 plus another 10 for numbers, and let's say another 4 for some punctuations like full stop, space, etc. So if you had 42 tones, you could actually have 1 tone for each letter, right? But what has happened is the number of tones are more, so your bandwidth is more. As a result, the noise coming into your receiver is also more. So you have to strike a balance somewhere. And this, what FT8 does is a very, very intelligent balance between that and a trade-off. So now what happens is that if you have, if you're sending out a message of where each character is represented by 6 bits, a combination of 6 zeros and ones, and each note, each tone gives you 3 bits, it will take you about 5 seconds or 26 flips of the tone to send out a 13-letter message, which is what an FT8 packet is. That 15 seconds thing is actually 13 letters. However, that takes 15 seconds, right? And the important thing here is that what happens if one of these zeros or ones does not go through, right? Instead of a 0, you think that it's a 1, and the computer does not detect it correctly, especially if you are going QRP. So there are ways of actually figuring out what has gone wrong. And one way of doing that is what you do in CW, right? You ask the other person to repeat what you're saying. So you could keep repeating it and say that, all right, repeat every message 3 times over. So I'm trying to send Alice and Bob, all right? And each time you see that the struck out letters are the ones which have been sent wrongly, okay? So what you do is you send it out 3 times and choose the 2 which agree and discard the 3rd which does not agree. So you see those 3 rows are the 3 times the same message has been transmitted. In the first one, instead of in the name of Alice, the E has actually come out as D, right? So 3 times you do this, and then you basically write it down, and then you find out what was, you basically choose the 2 best out of 3, right? It's like a vote. And in the bottom, you'll get Alice and Bob. But at times, that may not work. At times, they may not work because it's quite possible that all the 3 times you got some bits wrong on the same letter. So what do? First thing you need to know is whether this message that has come through has actually been the actual message which the other party has sent. And for that, what you do is something called CRC. Now I am going to, all right, that. Very complicated, don't bother about it. But essentially what you do is, you take the entire stream of zeros and ones and slice and dice and mash it together to generate another few bits. And each time you get a message, you do the same slicing, dicing, and mashing of the bits together to generate a few bits more, and they should add up. That's called the cyclic redundancy check. You can see what it's doing here. I don't understand it myself, but it works very well. Okay, so now, so that's actually one part of it. So you take this, 70, I think 70 odd bits, and add another 14 bits of the CRC check. So each time you get this message to the other side, they try generating the CRC back and see whether the two match up, right? Okay, now let's do a little bit of more of error flagging. So we count the number of, let's say, ones here. And each time you encounter a one, you say, she loves me or she loves me not. So in the first one, if you see, you say, loves me not, loves me not, loves me not, loves me. So you say that's a one, right? That's a parity check. That is essentially saying whether the number of ones are even or odd. Okay, but a better way is just to keep flipping between the two. In the second message, you again see, you start with a love me not, love me not, love me not, love me not. So there's a 50% chance that if you add this parity to the end of the message, you might be able to see whether the number of ones have come correctly or not. That is, if there were 4 ones, each time you flip from love to love me not, you are on love me not. But if 2 bits have gone wrong, it would again roll back to love me not, right? So just putting a parity, nor does it tell you which bit has gone wrong, right? It's just a check to say that these many number of zeros should have come, but the number of zeros have not added up and the number of ones have not added up there. So what you can do is this. You basically take 3 copies of the same message and slightly skew them up. And this time, you are doing this business of parity check, that is love me not, vertically, right? Vertically, you're doing it. So now what happens here is, in fact, let me just step down here and show you this. Now, you see that message there, right? And if that 1 has flipped to 0, this will not add up. And because the same thing is also shifted here, this will not add up and this will not add up. So it actually flags which bit has gone wrong, right? So you will know which bits have actually gone wrong and you can possibly flip them out. So by actually generating another whole series of parity checks, more than one parity checks, across for each parity bit you've chosen a different set of zeros and ones to check. So you can sort of cross-relate. For example, if I had organized the entire bit stream into a box and taken columns and rows and done a parity check on the rows and columns, and if a particular row and column say that the check is not right, you know that the one that's intersecting it, that's the one which has gone wrong, right? So this has a fancy name. It's called a low density parity check. We are done with this, right? Now you can all breathe easy. Okay. So you take the 77-bit message, add the 14-bit of CRC, and 83 bits of parity to it. That's your FT8 message. So as you can see, there's a lot of robustness built into the FT8 itself. And how do you know when it starts? Of course, you know that it starts every 15th of a second. That is at the top of the minute, 15th second, bottom of the minute, 45th second, and back to the top of the minute. But even there, because of propagation delays, you don't know exactly what time they will start transmitting, and everybody's watch is off by a couple of seconds. So there are certain sequence of tones that the computer can easily pick up, and those are put at the beginning, middle, and the end of the FT8 transmission. Okay, they're like, we always can hear ta 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 ta, ta 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 ta, right? So we know what that is. So it's like that for a computer, that they can figure out when the message is starting, because he can figure out that 31400652 is the third tone, first tone, fourth tone, 0th tone, sixth, fifth, and the second tone. So that's always repeated at the beginning, end, and middle of every FT8 transmission. So all this put together makes it very easy for the other side to reconstruct the message, and you always assume that some bits are missing. And those are put back by the parity check, and you know whether what you've put back is actually correct or not. Now, there's one more important thing here. We are assuming that we are able to do a 0 and 1, right, in terms of signal. But the signal is an analog thing. So at times it can be 0.8 and 0.25. So you'll say that anything below 0.5 is 0 and anything above 0.5 is 1, right? So you could keep doing that. And when you're trying to reconstruct a message, you can actually figure out and repeat it by lowering the threshold of what is a 0 or a 1 and try reconstructing the message back, which is what the deep mode in your FT8 does. It actually, tries various combinations of what is a 0 and 1 in terms of amplitude, and then figures out whether, the message is coming back or not. Anyway, so now here are our challenges. All stations are not always on. Band conditions are erratic. But what we are looking is for asynchronous communications, which we rarely do with us, right? Which means this communication doesn't have to happen in real time. It can take minutes, probably even hours. We are fine as long as the message comes across. Required for emergency, required for reliable communications, why not? And it's optimized for about 20 to 30 characters, which means 3 transmissions of FT8. Now, this is an analysis of message lengths of WhatsApp, right? Where you see that 34.36, which is about, the quadrant on your right, is just messages with 1 or 2 words. You say, okay, all right, no, not at all, or whatever. And 31% of the messages are with 3 to 5 words. So if you put those two together, your optimization has to be for messages which are about 20 to 30 characters. And that's what we do here. So this is how we do. So there's a concept called presence, which basically, in your instant messenger, you will see somebody's online, somebody's busy, somebody's away, etc. That's called presence. And the way all the messages coming out for presence are the messages which start with a plus sign, right? So you see here, VU to ESC plus VU to ESC, and I say MJ97, which is my grid. So I'm there. Or, you could actually add any text to it. You can say I'm ready or away, etc. So whenever you get on to the HF messenger, every 5 to 6 minutes, you broadcast this message out. And everybody else who receives it will put it against your contact. So that's how the contact list will work. That works on all your instant messaging systems, which is that this happens. And it should not be precisely every 5 minutes, because the other station who's trying to receive you and who's interested in contacting you might be transmitting at the same time. So after the 5th minute, approximately anywhere between 5th and 6th minute is when you transmit it. So that if somebody else was transmitting and the receiver as a result was not on, they can catch you on your next transmission, right? So, so now what happens is that if you're waiting, let's say, I was waiting to send a message to Jack. My receiver is on until I get a notification message from Jack that he has just turned his system on, and that's the time for me to start transmitting the message that's intended for him. And this is called a ladder diagram. And in telecom world, you always use party A, party B, also called Alice and Bob. So Alice is always the one who's trying to send the message to Bob or trying to contact Bob. So now here, the way it works is that Alice is in receive mode and waiting for a message to hear from Bob. Now, Bob may be on, but the propagation condition between Alice and Bob may not be open, right? The band may not be open between the two. So you just wait until you get an FT8 message from Bob saying that, I'm ready or whatever, that I'm on air. So that's a way to know that, the path works between the two. Okay. The first message that you send is a standard FT8 message, which is interpreted differently. So here I'm saying that, Bob, this is Alice and FX20, and I'll explain what FX is. So first, let's go from right to left with that FX20 business. 0 is always constant. We are not going to change it for this version of the messenger. Probably in the next version, we'll put a 1 or a 2 or whatever. 2 says that there are 2 messages. So your message is actually, 2 slots. So 2 FT8 transmissions will make up the entire message, right? And the FX is again a checksum. It's mathematically derived from the message, because you don't know which message you're talking about between 2 parties. I might have 5 messages piled up for Jack, and you don't know which of these messages this one is, right? So it's like an ID for a message, which is generated by summing up all the letters of that message itself. So there are 2 messages here. One says, are you ready to test new antenna, right? And I have replaced the spaces with underscores here just to make it clear. Both the messages are exactly 13 characters wide, and spaces are padded to make it into 13 characters wide, right? And if Bob receives it, Bob sends back my original header. So I know that Bob has received the message, right? It's as simple as that. Now, there's a bit of a trick to it. The message that's coming back from Bob actually has Bob's call sign first and Alice later. So Alice will know that, because Alice has not transmitted this, right, that it's a response to the actual message, right? So it's very simple. You basically wait for a notification message to come from the other party, and then you send a header, and the header has both the call signs of the sender and the recipient, followed by a checksum generated from about the message and the length of the message. You send the entire message out immediately after that. Okay. Now, on Bob's side, okay, I don't know about Bob, but if it was Jack, he'd have about 15 people transmitting messages to him at once. And all of them will start coming in simultaneously, right? And because they're all coming in simultaneously, the response to my message to Bob may not happen in real time, because he has to wait for all the messages to come in and then patiently, give the acknowledgement for all the messages back. So as a result, what happens is the response from Bob to Alice may actually take time, which is why I've put ellipses there. So you have to wait for about 5-6 minutes for your response to come back, or the message that you have sent to the recipient. Now, here we also make use of FT8's property that it can actually receive up to 50 messages simultaneously. So your incoming bandwidth is far higher than your outgoing bandwidth, right? But now, there are a lot of what ifs here. We are saying that this is a very reliable system, right? What happens if you miss the notification? Not much. You wait for the next notification to come in. And the reason you've missed the notification is that the HF path is not open between the two. Which, that's one of the reasons why we call it an HF messenger, right? It's very specific to the challenges of HF communications. What happens if the header doesn't make it to the other side? It's okay, right? You will just, unfortunately waste a lot of your power transmitting the next 2 slots, but the acknowledgement will never come back, so you're fine. What happens if you miss these 2 coming back? The same thing, the acknowledgement will not come back. The tricky part is, what if the acknowledgement doesn't come back, right? The other person has received it, said, yeah, I got you, and send the acknowledgement back, but you did not receive the acknowledgement. But what happens in that case is you will repeat the same message again after a while. And because you have a message ID that FX20, you will say, no, I already got this, and you will acknowledge it. You will not process it as a new message. So it will be the same message all over again, right? So that's actually all there is to it. it's just something which has been built on top of FT8. And right now we have code working just for my own SDR, which we have done, which is the ZBitX. It's still experimental, so it's on an experimental branch of our source code, but it looks like a messenger. It behaves like a messenger. It's actually very easy and really, really useful for us. I mean, just before we came in is when we stabilized it, and Sashi and I were constantly using this to communicate between us. I mean, he works about a few kilometers down the road, but nevertheless, we found that, and that's actually one of the worst things to do on 40 meters, which is you're always on skip, but somehow you do get through in about 15, 20 minutes with your messages. Which is why you will see, some messages have gotten through quickly. Some of them have taken a long time to get through. And if you see there that the messages that I have sent out to Sashi have ACK written, acknowledgement written over it, which means that these messages have made it through, right? The uppermost message has not yet made it through. So there's no acknowledgement against that. So, and on the left, you will see that all my contacts are there. And against them, for example, Sashi had set his status to busy, and that's busy there. And I can, you see that a button called presence, you can actually change it from CQ, meaning I'm open to contact with anybody, to saying I'm busy, I'm on air or whatever. There are a couple of, options there. I can add more call signs. And if I don't add the call sign explicitly, what will happen is that when I reboot the system, the messages from those that I have not saved will not be saved. So it just declutters my contact list. And I can click on a contact and press the post button and add leave a message behind. It's called post, not send, because it takes a little while for the messages to come across. So that's actually just about all. The status is still under test. And there's a branch of our source code called Messenger. If you know how to operate JIT, it's very easy. You just have to say JIT checkout Messenger, and it'll actually give you the entire source code for this. I've tried writing it much simpler than rest of the spaghetti code of ZBitX. We do need more testers and developers, and my problem is in India, it's just a couple of us testing it. I want to simulate and see what happens when about let's say 20 people are trying to message each other within the same bandwidth. So that still remains there. But my initial feel of building this on top of FT8 is very good. It's extremely useful. It's very useful, and actually this started by Bob Larkin. He wrote to me that he had gone on a hike with a QRP radio, and where he had gone to, there was no coverage, and he tried on CW to reach out to people just to say that he's okay. Nothing really happened to him, but he just couldn't get it across. And he came back and he's built this radio called Tiny 10. I think I've posted about it as well on Bitex list and a couple of other lists, where he said, I just want to get one 13-character message across on FT8 to somebody saying that I'm all right. But I couldn't do it there because he just carried a CW rig. And this sort of developed out of that idea. And as you can see, because it's a communication protocol, it's less of programming, far, far more of testing. And we've spent at least about probably 100 hours just testing it and figuring things out. And that's where it requires two people to do this, which is why this is the first time I'm presenting a paper with Sashi here, because you need to get inside the mind of the protocol to figure out what's happening. But it's very interesting, and unfortunately it's not CWDXing, but it's something that's very useful. Thank you.
Any questions?
Yeah, thank you. Very interesting.
Have you published a specification on this so it could be, coded for other platforms as well?
Sure. In fact, the specification is ready and it will be published in the next QRP quarterly. You'll have the entire thing. Yeah. The entire paper will be published along with the RFC, so to say.
I was just wondering if it's available for the SBitX also.
Sure, absolutely. I mean, the code base is the same. Yeah.
One thing I was wondering with the 4-digit checksum, how likely are collisions in terms of
Well, I mean, each digit represents about 1 of 40. So it's 40 into 40, which is 1600, right? So the possibility of it is that the same message, which is 1 out of 1600, has been repeated, but it's not that good. And I'll tell you why. If I'm just saying okay to everything, you don't know which okay I've said to which message, right? It's the same message going over and over again. So that actually is a problem. But on the other hand, we figured that if the message, frequently transmitted message, could be represented by the checksum, which is what Q codes do, right? Q codes are essentially fill in the blanks. For example, if I'm saying, hi, Sasi, how are you? As usual, let's meet on Wednesday. And I say that every week, right? Then the checksum itself is enough to retrieve that message back from the cache, right? So I was thinking about that as well, but we'll leave it. That's what, by the way, CW schema does. Sorry, Steve. Yeah.
Yeah, I have a further question about that checksum code. Why not use a monotonically increasing number or even a random number for that, especially if that checksum code indicates a message ID between two participants? It does seem like the probability distribution on a checksum code is flawed.
Where are you? Sorry, can you just, oh, sorry. Okay, yeah. I think, okay, we considered that, right? In fact, because a lot of this learning has come from an internet protocol called SIP, Session Initiation Protocol, that I worked on in IETF. But what I realized is that the message integrity here is a problem, which is not there on the internet, which is why we needed the checksum. So we tried both, right? And the auto increment message ID required you to sync the message ID on both ends, which was becoming difficult to handle. But if it was always between two parties, that's the way to go, right? Another thing which the message with the checksum could do in future is authenticate the message. So for example, we have a public-private key of sorts, right? I could also throw that into the mix of the checksum to sort of sign the message saying that it's actually come from me. But that's for future. I mean, it's not even legal. I'm not even sure whether it's legal to do that now. Yeah, it's not good because I had to constrain it within 13 letters, right? That was the problem. So probably, something better could be done. For example, if the party A and party B could be conjugated into one ID, right? That's one way to go. Yeah. Sure.
Interesting, Farhan. And interesting you said SIP. I thought you were going to talk about the interplanetary stuff the IETF is doing.
Yeah.
This is a serious protocol.
Yes.
But my question is, you still require time to make this work, which is really great, except that if the world lost its timing infrastructure, this wouldn't work. Have you considered expanding the protocol to make it, which is quite a simple expansion, to make it operate without time reference at both ends?
Actually, the protocol itself doesn't require that, okay? Because, let me just show you this why. So if I can go back here. Now here, if you see the header, the middle, and the tail, okay? Those are actually what are called as Costas arrays. So Costas arrays are patterns made by tones, which are very easy to detect. So there is one implementation which constantly keeps scanning for this and uses that itself to synchronize the time. But what happens with that is that you are synchronized just between Alice and Bob. But what if there's a Charlie, there's an Eve who's eavesdropping on you or whatever. So yes, yeah.
Yes, is the acknowledge unique to the individual person, or if multiple people are using this, can acknowledge be one for many?
Okay, good question. I was hoping someone wouldn't ask this, but but the thing is that there is no provision right now for a group chat. Okay, and the acknowledgements have to be done between the party A and party B because you know who that. It's a directed message, right? It's not a broadcast message, and as a result, doing reliable broadcast, multi-party messaging is very difficult on RF. It's really difficult. I mean, a lot of three-letter organizations would be interested if we could, do it efficiently and quickly and simply. So that's one. The other thing which this can do is, by the way, do internet linking. So, for example, if I can't get to USA, which is very often the case on FT8, there's another station in between which can relay me back out, but we haven't expanded the protocol to do that. So that's one of the other options, which is why we require the acknowledgement in place. Thank you.